Hello, everyone. Welcome to this post-coffee pre-lunch session. We have two speakers in this session. The first speaker is Golam Shaifullah. He'll be talking about not just cosmology with pulsar timing arrays. So you have 45 minutes. I'll warn you, it's 40 plus 5. Yeah. I'll warn you after 35. Right. There is a clock ticking here.
All right, thank you. Hi, everyone. I'm Golam. I'm a postdoc at the University of Milano Bicocca in Milan, of course. And I work mostly with pulsar timing arrays, although by training and by education, I am basically a pulsar astronomer, so I spend a lot of time observing pulsars, and that's how I got into the PTA game. So I have 40 minutes, and I have 48 slides. Let's see if I make this challenge. Okay. When I was preparing this talk, I wasn't quite sure of the audience, so the content is going to jump a little bit between being very introductory and being quite heavy on the results that I present. But thankfully for me, Srikumar has introduced a huge amount of the things that I would have needed to otherwise. So I'm just going to flash through some of the PTA results that I have and not bother to explain why they are the way they are, because that's already been covered in the morning session. Okay, moving on. So as I said, I'm a pulsar astronomer, and PTAs are all about pulsars. But what are pulsars? Pulsars are, for the purposes of our experiment, we just treat pulsars as these fantastic flywheels in space which are spinning around, putting out a beam of light, and the beam of light crosses my detector on Earth, produces a tick or a pulse. These pulses tend to be quite regular, in fact, so regular that we can treat the ticks as if it were a very nice clock. And the other thing we can do is we have fantastic clocks on Earth as well, which are very good at timing or producing ticks on very regular ticks on very short intervals. And we can use those to time tag the pulses that I observe from a distant pulsar and convert the pulses of the pulsar to a time of arrival. Or for each group of photons in a pulse from a pulsar, I can assign a time of arrival to that pulsar as measured at Earth. So that's the TOA. Some of this jargon requires a little bit of background, so that's why some of the introductory material. But yeah, pulsars, of course, were discovered by one of my favorite people on the planet, Professor Jocelyn Bell Burnell, who I just met last month. I'm super kicked about it. But moving on. Okay, I've done something. Right. So once you have these times of arrival, what you can do is you can construct these very nice and somewhat, in the context of the complicated algebra and geometry that we've just discussed this morning, fairly simplistic models of how these TOAs are being generated, or how the time series of the pulses are being generated by this distant rotating object. You can assign it a place in the sky if it has some proper motion on the plane of the sky, which go into the astrometric properties. You can ask the question if it's a spinning ball of something and it has a beam pointing out of it, how fast does it rotate? How fast does that rotation change? That's the properties of the pulsar rotation. And if it has a companion, if it has one or more companions, how does that system operate? You can put that into a binary or a more complicated model. And that's what I mean by the binary properties of the pulsar. Apart from these simplistic big giant blocks, you also need to factor in that radio emission from the pulsar as it passes through the ionized interstellar medium and reaches us. It will undergo frequency dispersion. So higher frequencies will arrive slightly before lower frequencies. And that needs to be corrected for, and that's the dispersive delay that is down there. Apart from all of these, there could be other stochastic low frequency processes which gradually change the time of arrival over spans of years to tens of years. And that's what red noise processes refers to. Once you have these things, you can take the observations and fit them against a model of the pulse, which is the template. And then you have this polynomial, which has the big blocks that I just mentioned, within which there are a set of parameters. But the fun thing is, once you have this, you can predict precisely when the next pulse will arrive, or when you expect the next pulse to arrive. When you have this model, you just subtract it off from your observed time series, and you're left behind with a set of timing residuals. And this is where the entire focus of PTA analysis goes into, because this is fairly deterministic. If you have most of the components in place, and you need to improve these things over time, you can just do that by observing the pulsar for longer and longer. You want to do very high precision experiments in time. You want to measure the ticks of a clock, which is a kiloparsec away, with very, very high precision, because you want to look at things like gravitational waves. So why, or what are the best clocks to choose? We know about 3,600 pulsars, a bit more than that at this point, but a lot of them tend to be spinning at periods of a second or more. But they also show a lot of intrinsic behavior, which we don't want in our clock. So if we leave those out and we move downwards towards this smaller island of pulsars called millisecond pulsars, we get fantastic repeatability between their pulses, and very, very limited amount of the jittery effects that you get up here, which makes these millisecond pulsars excellent clocks on large timescales. In fact, approaching the kind of precision or the lack of deviation from predicted behavior, which is comparable to atomic clocks on Earth, but at very different timescales, of course. So once we have these basic building blocks in place, I'm looking at a millisecond pulsar, which is far away. What I can do is, I can ask the question, if I have simply the millisecond pulsar hanging out in space, what do the timing residuals look like? And that's just Gaussian distributed, some fuzzy noise, nothing too weird happening. And then I can recall for myself that the universe isn't a void. There are lots of things hanging around. One of the cool things that are hanging around are these pairs of supermassive binary black holes, which, as they orbit around each other over somewhat large separations, they will emit gravitational waves. Those gravitational waves will modify this Gaussian distributed residuals in a very specific way. But the universe has not one, or we expect that the universe has more than one of these supermassive binary black hole pairs, and we expect a very, very large number of them to actually exist out there. So what we would see is not a simple sine wave from one of these sources, but the coherent superposition of the signal from many, many, many sources. And that would produce a very nice and distinct feature in our data. Okay, great, fantastic. That's a very simple experiment to do. Why haven't you done that already? Because when you go to real data, that's a simulation of, well, that's just real data. If you look at the real timing residuals of pulsars, you cannot really see too many features out there. The features that are visible in this particular plot, do we know where those come from? So looking at one pulsar, therefore, is not a very smart way of searching for these signals of interest, which at this point in time are gravitational waves. We've already established that we want to use millisecond pulsars, because they are less noisy, but also because if you observe a millisecond pulsar for 10 minutes, you have the fact that it's rotating a few hundred times every second, and in 10 minutes, you've put together many, many rotations. So the profile that you collect in 10 minutes will be stacked, and it will become super loud and super stable. And then when you compare the profile, say, observed on this date, and then go 10 years later, 20 years later, and look at the profile on this date, you will find that the profile is very, very similar. That means you can do cross-correlation and time tagging very, very accurately, and you can model any effects in between this time period very, very precisely. And the reason we don't want to use each individual pulse is basically because we are interested in an experiment which lasts 20 years, 30 years, 50 years. And as I said, pulsars are rotating. Pulsars can rotate up to several hundred times a second. And you don't really care about the per second behavior at this point, except it'll pop up back as an annoyance. So what we do is we put together many pulsars, and then we collect the data on Earth with usually one telescope or a group of telescopes. And we look for signals that are cross-correlated amongst the pulsars. And that's the concept of the pulsar timing array. So the pulsar timing array is a strange detector in the sense that you're observing astrophysical objects, you're monitoring astrophysical objects. So your detector is not really the telescope or the instrument you built on Earth, it's the program of monitoring several pulsars over a period of time. And that's something to keep in mind, that this is really the detector, and that's what we need to characterize. I hope we move on. Okay, so what is the signal we are interested in? As I said, we are going to observe a number of pulsars distributed uniformly on the sky, hopefully. And so this is a plot of pulsars from the European pulsar timing array, which is the one I work most with. There are a bunch of pulsars on the sky scattered randomly. I've modeled, or actually have mapped the sensitivity of this particular distribution of skies at a given frequency. And you can see that where there are more pulsars, we tend to be slightly more sensitive. That's all great and fantastic, but this is a very, very hypothetical idea. But once you have these pulsars and you have gravitational waves which are sort of passing through the plane of the slide or the screen, and I have a set of pulsars distributed in this very weird fashion, what I will find is that when I go to two pulsars lying on the same side, gravitational wave will produce a strongly correlated signal. But as you go to orthogonal directions, it becomes anti-correlated. But then when you go over to the other side, you start to get correlated signals again, but you have this fact that the gravitational wave does not produce the exact same effect at the pulsar here as opposed to the pulsar here. So the correlation doesn't quite recover all the way up there. That's the famous Hellings and Lowndes correlation. And this is one of the key signatures that we look for in PTAs to ensure that the signal we are recovering is really a gravitational wave signal and not a isotropic gravitational wave background. It doesn't really matter how you do it. In fact, if you go read that paper, it's just a plane wave, so it would work for either case. But also you can find much more interesting and fun conversations in this little article by Joe and Bruce. Sorry? That's just a weird way of trying to show the strength of the correlation as well. So it goes from, that's the separation angle. So it's just the x-axis also plotted back on the curve. So it's just points, and this is low angular separation, this is high angular separation, which is just this x-axis. It doesn't make a difference. So how do you build a PTA? The secret sauce is that you find a pulsar, and you find a nominal dispersion measure and a nominal rotation period, and then you start to observe it. Every single pulse we observe is very faint, it's dispersed as it passes through the interstellar medium. So what we do is we first de-disperse it, we make it sort of straight in this fun cartoon that I'm making. We make each pulse stand up straight in terms of frequency versus rotational phase, stack a whole bunch of them to produce a very loud pulse. This is what we can use to construct the stable template or the expected profile on every rotation, which is this one. But the average profile on every rotation is just this thing. So between this template and the average profile, then you can do cross correlation in the Fourier domain to find, sorry, there's a secret here, which I'll probably refer to in the next slide, but you need a time associated with every rotational phase bin, which will happen for the template as well. But then once you have this, you can choose a nominal time on the template, and you can try to find the time at which the same phase bin arrived in the actual data. That's what I mean by cross correlation. We do this in the Fourier domain, and we find a TOA for each observation reference to this template. And then we apply our model, we refit to include or improve parameter values, and we're left behind with a set of residuals. We take these very, very long sets of timing residuals, and this is where PTAs live. This is where all of our signal searches go on. Okay. So once you've gone through this cycle a few times, maybe over 10 years or 15 years, what you can do is you can construct this kind of plot where you have, say, a bunch of pulsars, and this is the data release for the EPTA, where we have 25 pulsars which have been observed over something of the order of 24 years. And we have observations taken with many, many different telescopes and observing systems, a bit beside the point, but just to show you how complex the data looks. This is the kind of data set that you end up with. You do some sort of data analysis magic, let's leave it at that, to make everything line up and fit together and produce the very, very precise deterministic timing models that you have. But then even if you have the deterministic timing models, the problem is that you have some chaotic stuff happening in the interstellar medium, as well as the solar wind, which is another ionized plasma hanging out. For the purposes of PTAs, let's just consider it to be an ionized medium that's producing some extra disturbance. You have systematics which could come in either at the observing system itself or in your recording system. And to get to PTA quality data, what we need to do is figure out what these noise sources are. Because what we want to do is we want to make sure our timing residuals are able to are modeled sufficiently well with both the deterministic and the stochastic components that would come in from any of these blocks, so that we are able to probe the gravitational waves that we are interested in. And we do this using, in most modern PTA analysis, we have switched to almost fully Bayesian analysis pipelines. And before we go on to the Bayesian analysis, a little bit of a disclaimer here. As I mentioned, I'm an observer, so I'm not going to be very heavy on the equations, but I will occasionally refer to things. So what we do is we construct the likelihood function, which contains the timing residuals. Here we've already simplified the thing by taking out all the deterministic parts. That's where all the deterministic stuff goes in. Sorry, actually, this was for a slightly different equation. So maybe you can ignore that. But this S would contain all deterministic signals, not just gravitational signals from individually resolvable SMDHPs. But the giant product we end up at the end is this noise variance covariance matrix, which has this size n by n, where n is the number of observations. And that variance covariance matrix, what it contains within it is terms which describe system noise, so white noise, any low frequency process, which is the red noise. In this case, we can consider this to be noise in the observed rotational period of the pulsar. Then there's this thing called dispersion noise, because the interstellar medium is not stable, or it's a turbulent medium, so it doesn't have a fully deterministic model. So some of the things I did earlier are not enough to model that out. And then you can have any other source of stochastic noise. It could be gravitational waves, it could be something else. Once you've built this, so how do the noise signals look like? Here is an example. Up there is an example of a red noise process in one of the pulsars in the EPTA DR2. And down there is a dispersion measure variation. So these are not physically measured processes. These are the reconstructed time domain representations from this awkward power law formulation that we use, where we translate everything into the frequency domain. We say we have power at different frequency bins, and we fit power laws to that. I'll show an example, hopefully, at some point, of what that spectrum looks like. And once you have the, you can constrain, or rather, these came from these analyses where we have constrained the power law models for the red noise process and a DM process. If you want more details on this, that's the paper to look at. And of course, there are papers from NANO-Grav, papers from PPTA, papers from the MIR-time, and there should be a forthcoming paper from the Chinese PTA as well. And of course, there are also papers from the Indian PTA. They have just submitted their DR2 paper, the noise analysis paper. I think there is noise analysis in the DR2 paper, but there will be other work coming up from the Indian PTA as well. So you've already seen this. This is a bit old, right? Most people in this room know, or you've already seen the announcements made last year, almost 18 months ago at this point, where we claim to have found very strong evidence for an HD correlated process in our data. And this was a claim made by 5 PTAs, although the EPTA and NPTA, we work together. So we combined our data and we make the claim based off the combined data, not of the individual PTA data sets. The final posteriors look kind of not too much in contest with one another, except for the CPTA, but then there are some caveats, which is that the CPTA is a very small data set at this point in time. So some of these things, so the blue 2D histogram is not quite the same histogram as the rest of these histograms. So don't take this at face value. And this is just a comparative, you can even call it a cartoon. So once you have these, what you can do is you can ask what is the significance of the signal. And this is of that order, which is below the 5 sigma detection threshold that we set for ourselves as a detection claim limit. And the other discerning feature is that this amplitude is really loud and the spectrum is very flat. Which makes, okay, that's just to drive home the point that we haven't made a detection claim, although you will find a lot of papers claiming that PTAs have made a detection. We haven't ourselves said that yet. We then also took the posteriors from the individual PTAs, or the data from the individual PTAs, and then tried to do a very quick comparison of are all the PTAs in agreement with each other? Because if you look at the individual papers, there seems to be some sort of tension. And we find that there isn't really a big amount of tension between us. I'm trying to speed up because, but it still remains that the amplitude is really loud and it's a very, very flat spectrum. This doesn't compare very well with astrophysical implications, as has been mentioned earlier. I'm not going to talk too much about this, except to say that it doesn't compare well with models. We tried that, but you can change the models around a bit. And in fact, if you get lucky, even without changing things too much, you just draw a different realization of the universe we are in, and you can find a discrete form of the gravitational wave background, and it would fit almost perfectly the EPT data. That's not to say that's the true one, because that's just a simulation. But the challenge remains that it isn't quite in agreement, especially at the most constraining frequency bin of 1/10 years. It seems like PTAs are not happy with traditional models. You can try to fix those models in several ways. I don't have time to even stay on these. But you can use these tricks of changing how the SMBHP is generated. You can look at environmental effects, stellar hardening. You can ask, are we misestimating the HT because we don't quite know the distribution of supermassive black hole binaries in our universe, and it could be one of many possible universes. So the HT is actually not that thin line that I showed. It must be a band, as shown by Bruce Allen and others. But it doesn't quite resolve this question. So naturally, and as you've just heard in the morning lecture, the natural question to ask is, what about other sources of backgrounds? So cosmological sources are fantastic backgrounds, especially at nanohertz frequencies as well. So in the EPTA DR2 data set, we also tried to fit for cosmological backgrounds. If we consider inflationary gravitational wave backgrounds, we find somewhat constraining results, but the maximum likelihood values are a little bit in tension with a slow roll inflation model. So that needs to be factored in when you look at this result, and we say that in the paper. You can ask the question, is this background produced by cosmic strings? You've also heard about this between yesterday and today, and you'll hear more about strings throughout the next 2 weeks. So I won't dive too much into that. But we find that between some of the most updated models, I say updated, but that one's from 2010, that one's from 2014. But it has been refitted to LVK data. So we find that there isn't a great choice to make yet. But you can then ask the question, what about perturbations in the early universe? And you can ask questions like magnetic fields, primordial magnetic fields. So Alberto, I believe, will be talking at some point during the next 2 weeks. So I would advise you watch out for his talk, where because he co-led some of this work within the paper. And again, nothing really constraining, especially for the more, let's say, exotic models. You can also ask curvature questions about, can curvature perturbations be the source of this background? You heard a fantastic discussion of this just half an hour ago, so I won't dive deep into it, but we will. I'll just pause to show that the DR2, because of its very, very long time span, is starting to get to the region where even with just Firas and without even the Pixie bounds yet, we might be able to start constraining some of the models, especially in work which I just realized this morning. Srikumar is one of the co-authors of. All right, I cite cosmology. That's all I'm going to talk about in terms of cosmology, because I realized in the middle of the night last night that you're going to hear a lot about the actual physics of these from much better, much more renowned experts than I am in any of these topics. So I won't dive deep into it, but I'd advise you to take a look at the EPTA paper 4, which is where we dive into the astrophysical and cosmological backgrounds and where we've done these things in different blocks. But, for the sake of the audience, which is at this point, I'm worried if you're just falling asleep. Let's do some fun stuff. So, does that sound fun? No. Okay. I try. So the thing is, I have this fantastic network of pulsars, which I'm observing in the galaxy. So far, I'm looking at only the pulses, and I'm asking the question, can I only look for signals in between the pulses because of some sort of stochastic gravitational background? But you can also have other sources of stochastic fluctuations in the pulse periods. one of those could be dark matter. If you scatter bits of dark matter around in the galaxy, you could be affected, or your pulses could be affected as they propagate through the field of a dark matter. Of course, answering this question has very important and relevant bearings on physics that you are interested in. We did this with the EPTA DR2 as well, again. And if you look at only the timing data, if you look at the pulses and you search for signals from ultralight dark matter, we are able to produce the strongest constraint on the ultralight dark matter density. Again, because we have this extended timing baseline of 25 years, we are able to probe down to a much lower energy range. And that tells us that we cannot have more than 70% of the needed ultralight dark matter as far as PTAs are concerned. So we can rule out many of the models for ultralight dark matter production. And that led to the EPTA paper, which was officially called, internally called the paper 6, but it appeared separately in a different journal because we realized the target audience might be very different from the one reading the rest of the papers. And that's where you will find this result. There is a letter which follows up on this and reworks the paper a little bit, again by Clement Esmarra and others. So I'd advise you to take a look at that one. But can we take this a little bit further? Is there something else that I can do with pulsars or PTA data that lets me constrain ultralight dark matter in a more interesting way? So one of the things that I did not mention is that the emission from pulsars is highly linearly polarized. Often there are pulsars where it's not, but very often we find that the emission is highly linearly polarized. And what that does is it allows us to construct a Faraday rotation experiment where we can measure the rotation of the plane of the polarized light as it's passing through any medium that's in between us and the pulsar. Now, this could be just magnetic fields in the galaxy, which is what we often use or often model. But you could also have additional rotations because of ultralight dark matter. And what this will do is this will make your residuals wiggle around in somewhat monochromatic way, especially if you use the fuzzy dark matter approximation. And if you were to construct, so suppose these are actual timing residuals, so you won't find this feature, but suppose you have fuzzy dark matter interacting with your pulses, and then the TOA, and you took the TOAs and you constructed a Lomskargil periodogram. If there was a real signal in there, you would find a very nice peak in your Lomskargil periodogram. So this feature, the reason this exists is because we assume that the dark matter is coupled with the rest of the universe in specific ways. Those are the papers to dig out if you want to check how that coupling works. But if we have that coupling, we can find for the let's assume this is a vector which specifies the angle at which the plane polarized light from each pulsar is received at the beginning of the observation. And that angle will be changed by the dark matter in this very constant, so monochromatic way across. And we should be able to see this as a change in the plane of this plane polarized light. Wow, okay, that wasn't the intention. Maybe that's the computer telling me I don't have time. Okay, You just got to see my talk backwards. Right. So maybe here. Right. So the okay. This particular feature is somewhat dependent on how dark matter is distributed in the galaxy, and this other thing is that no matter how you constrain these models, or which model you assume, because we are not constraining the models yet, just assuming some way of distributing dark matter in the galaxy, you look at the signal in different pulsars, and if you try to construct the correlation over pulsar pairs, you would find that the correlation is of a constant type or a fractional term on top, which we call the fractional monopolar term, because at each pulsar, the dark matter is producing this change, and at Earth, for each pulsar, the dark matter is again producing this change in the plane of the plane polarized light. But the change at each pulsar is uncorrelated across pulsars, whereas the change at Earth, when you observe this thing, is correlated for all the pulsars. So that's why you have a constant term, which is the signal, and this is the uncorrelated thing, which you see differently depending on where you're looking in the galaxy. So the point of putting that up there is what we did in analysis is not to consider the ultralight dark matter as a correlated signal across all our pulsars. We search for it in individual pulsars and then sum everything together. And the way we do that is we observe the plane of the plane polarized light in each pulsar beam for every observation. And we take the Stokes intensity profile. Stokes size plotted here just to make things a bit simple. We line them up, and the plane of the plane polarized light is changing in this very specific way, which is this polarization angle, which is specified by the polarization angle. And what we are trying to find is the change in the polarization angle over a number of observations as compared to a standard template. And eventually what we should end up is with this delta PA, which is just telling you how the plane of the plane polarized light was modified by this constant signal. Unfortunately, one of our big challenges is that this is not the only source which can change the plane of the plane polarized light. As I mentioned, the galaxy itself can introduce some magnetic fields in the galaxy itself can introduce some Faraday rotation, but also the ionosphere can introduce Faraday rotation. To correct for the ionosphere, we use a method we developed back in 2013, or from 2013 onwards, which has been recently published. And we try to model out the effects of the ionosphere, because if we don't do this, as you can see, we would be very, very strongly dominated by these huge effects at 1/1 year, which is the annual period, and 1/11 years, which is this period of the solar cycle. And because the ionosphere is very heavily influenced by the sun, this also shows up as a giant peak. If there are questions about that, I can deal with it later because I'm really low on time. The other challenge in the data is that you would expect that when you observe the same pulsar with the same telescope over a number of days or years, you actually measure the same thing, or you retrieve back the same quantities. But it so happens that someone might change a cable and switch around cables at some point, which means your PA curves, instead of looking like the familiar S shape, can suddenly become an inverse S, and then you can spend a lot of time as a young PhD student breaking your head against the wall. And we've done that, we figured that out, and we've corrected everything. So now we have these very nice PA curves, but we had to rule out some of the things because it's, we tend to be overcautious. We drop observations when we cannot confirm that it is indeed tainted by an effect that we know someone introduced somewhere along the data processing pipeline. Once we have the PAs, once we have the polarization angle change over the rotational phase, we construct the template and subtract off the templates to give us a sorry, right, that's just a repetition of what I just said. For each observing epoch, we construct these polarization angles. We subtract off the template, we get the delta PA, and then we perform a weighted average of the delta PA for each epoch to produce these data points. And again, if the fuzzy dark matter was in here, what we expected to see was a nice big giant sine wave, or something that's sinusoidal. You can argue there's something in there, and hopefully there's something in there. But these are our data points. So these PA residuals are the equivalent of the timing residuals of the PTA domain. Okay, I'm a bit out of time, so I'll steal some time from the question if that's okay with the chief. Right. I won't dwell too long, but if you took these data points and you did the first analysis you could think of, which is to construct either frequentist or, in this case, Bayesian periodograms, you would again end up with these strong peaks, and that's what we found in some of our pulsars. So it was clear that we needed additional corrections. So we expand our Bayesian model to include, to account for the fact that it is really challenging to model the ionosphere properly. Even when you have a lot of data, there are these really difficult to model features in the data. So if you expand the Bayesian formalism to include that effect, we have now modeled out the 1 year and the 11-year cycle. And what we are left with is a very nice peak. This is for one of the pulsars. And if you do this on a per pulsar basis, and then you average them all up, you get this very nice constraint on the coupling constant, which starts to look really interesting. Based on this analysis, we can now go back into the frequency domain and start to make some of the plots you've seen before, and try to make a plot of what the coupling constant looks like as a function of the frequency, and compare them with constraints from other experiments. So effectively, colored regions imply things that are ruled in. So this is ruled out. And we find ourselves in this very nice, sorry, that's not correct. These are setting upper limits. So Planck still has the deepest upper limit, but PTAs are starting to set a very interesting upper limit as well. And a very similar experiment has been carried out by a team in the Parkes pulsar timing array, and their limit is also on there. And we find that we are able to constrain the ultralight axions fairly confidently using PTA data. But of course, at this point, things are not as constraining as we would like it to be. There is room to continue observing, and hopefully we will get to the point that one day we will actually get into the regime of very well constrained frequency bins and start to resolve some of these massive open questions. These are plots I've shamelessly just stolen from John Ellis's paper exploring the NANO-Grav spectrum, but similar work has been done with the APTA. It should be appearing soonish. And we find that indeed PTAs there are many ways in which PTAs can probe beyond the standard astrophysical models, and there's a lot of exciting science to be done, which, okay, I'll skip over this because this is rather long, and I'll stop here, which is basically to say that none of this will be done by, let's say, most of the old people in the room, because as I said, it takes 10 years to gather that data. I might spend the next 10 years of my life, if I'm lucky, gathering that data, polishing it up, but someone in this room needs to come along and analyze that data. So GWEX is an effort by some people across the whole gravitational wave background spectrum, where we are trying to put together early career scientists across the spectrum. If you do gravitational wave research, even if it's theory at this point, feel free to reach out, check out the website. Our aim is to increase crosstalk between different parts of the waveband so that we can figure out what are the most interesting experiments that you are interested in. We also function as your friendly advisors. We talk about careers, we talk about mental health, and we do a whole bunch of other stuff. Thank you.
We have time for a couple of questions. Is the microphone? Okay, please go ahead. Turn it on.
Oh, hello. So you showed the model that explains why the polarization changes if the pulsar passes through dark matter. But you also mentioned the frequency can get disturbed, the noise can be introduced if it's passing through the dark matter. Can you mention the mechanism by which it does?
So it's basically the same mechanism. You have your fuzzy dark matter, which you're considering as a wave. And that wave is perturbing the pulsars that are sitting on top of that wave. So it's exactly this, conceptually, it's exactly the same thing as gravitational waves are doing. Because gravitational waves are just jiggling the pulsars around, and that's changing how the pulses reach us. And if you replace that with any other wave, it's exactly the same trick, right? So that's why the pulses would also get shifted by the same wave dark matter. As long as you agree to some of the constraints that we have to apply when we talk about dark matter interactions with the rest of the universe, the logic holds. We haven't tried any searches with heavy dark matter, and I don't, again, I'm not the expert in dark matter, much less heavy dark matter. But if there is an experiment, I'm sure some clever people will. The data is accessible to everyone. If you want, I can show you how to access the EPTA, PPTA, NANO-Grav data. Feel free to try out a search.
Maybe one last question. Okay, if there are no questions, let's thank Golam.